The night sky holds a secret, a universe hidden in plain sight. A cosmic trick of the light, predicted by Einstein, reveals galaxies we should never be able to see. This phenomenon is called gravitational lensing, and it has fundamentally reshaped our understanding of everything. By the end of this journey, you will understand how we use warped starlight to weigh the invisible and see the first lights of creation. What happens when a galaxy cluster bends the fabric of space itself, and how can a distant supernova appear to us more than once? The answers force us to rethink what is real and what is just a reflection. What does it mean to see the universe not with our eyes, but through the logic of gravity itself? Place a wine glass on a patterned tablecloth and look through its base. The straight lines behind it will bend and stretch, creating a warped, circular version of the pattern. This everyday illusion is a perfect doorway into the grandest trick in the cosmos. In space, the wine glass is a galaxy or a cluster of galaxies, an object of immense mass. The tablecloth is the fabric of spacetime itself, and the light from a distant object, a galaxy even farther away, is forced to follow the curves of that distorted fabric on its journey to us. The result is not a simple blur, but a precise, predictable distortion. We call this cosmic mirage gravitational lensing, and it is not magic. It is the universe operating exactly as Einstein said it must. His theory of general relativity gave us a new way to see gravity. It is not a mysterious force pulling across empty space, but rather the consequence of mass bending the very stage upon which everything plays out. A massive object creates a depression in space-time, like a bowling ball resting on a taut rubber sheet. When light from a distant star or galaxy travels through this warped region, its path is no longer a straight line. It follows the curve, bending around the massive object. To our telescopes, it appears as if the light is coming from a slightly different place in the sky, or sometimes from multiple places at once. This bending is the core of the lensing effect. We see this play out in three distinct ways, each revealing a different layer of the hidden universe. The most dramatic is strong lensing. This happens when the alignment between a distant light source, a massive foreground object like a galaxy cluster, and our telescope is nearly perfect. The result is breathtaking. We see the distant galaxy stretched and smeared into brilliant arcs of light, or even complete rings encircling the foreground cluster. These are Einstein rings, named for the man who predicted their possibility. They are not objects but mirages, multiple distorted images of the same single galaxy wrapped around the cosmic lens. When the alignment is less perfect, we see weak lensing. Here, the distortions are far more subtle. A background galaxy might appear just slightly more stretched or elliptical than it truly is. By itself, this tiny distortion tells us nothing. But when we measure the shapes of hundreds of thousands, even millions, of distant galaxies across a patch of sky, a pattern emerges. Their collective, slight distortions map out the invisible gravitational landscape of all the matter, seen and unseen, that lies between them and us. It is like seeing the faint ripples on the surface of a pond and deducing the shape of the unseen stones at the bottom. The third type feels almost like a cosmic blink. Microlensing occurs when a single, compact object like a star or even a planet drifts directly in front of a more distant star. The foreground object's gravity acts as a tiny, magnifying lens, causing the background star to temporarily brighten and then fade as the alignment shifts. This fleeting signal can reveal objects that emit no light of their own, solitary worlds wandering the void between stars. Each of these phenomena, from the majestic rings to the statistical whisper of weak lensing to the brief flash of microlensing, is a different key. And together, they are unlocking doors to parts of the cosmos we were never supposed to see. But Einstein, for all his brilliance, was also a skeptic of his own prediction. He calculated the precise mathematics of this bending light in 1915, yet in a scientific paper a year later, he concluded the phenomenon was simply too faint, too improbable to ever be seen from Earth. For decades, gravitational lensing remained a beautiful idea trapped in equations, a ghost in the machinery of the universe. The cosmos, however, had other plans. The first real evidence arrived in 1979, not with a dramatic ring, but with a cosmic twin. Astronomers pointed their telescopes at a brilliant object known as a quasar, an intensely bright galactic core fueled by a supermassive black hole. They found two identical quasars, impossibly close together in the sky, emitting the same light at the exact same distance. The only logical explanation was that they were not two objects at all, but two images of a single, more distant quasar, its light split and bent by the gravity of an unseen galaxy in between. This object Q0957+561 was the first confirmed gravitational lens. It was proof that the universe was playing this trick on us. Then came the icon. In 1985, astronomers discovered something even more extraordinary. A single, distant quasar appeared not as a double, but as a perfect cross of four brilliant points of light, arranged symmetrically around the faint glow of a foreground galaxy. They called it Einstein's cross. Here was the smoking gun, a configuration so precise and so elegant it could only be explained by the warping of spacetime, exactly as Einstein had described. This was no longer just evidence, it was a demonstration. The universe had built a perfect laboratory to showcase the rules of general relativity on the grandest possible scale. With these discoveries, gravitational lensing was transformed. It stepped out of the realm of pure theory and became a practical, powerful tool. Astronomers realized they were not just looking at strange mirages, they were holding a new kind of telescope, one built from gravity itself. The question was no longer if the effect was real, but what profound secrets could this cosmic lens now reveal to us? The faintest glimmers from the edge of time pose an impossible challenge. Even our most powerful telescopes, like Hubble or the James Webb, have fundamental limits. Their mirrors can only collect so much light, and the universe's first galaxies are not just far away, they are desperately dim, their light stretched and diluted by billions of years of cosmic expansion. We are trying to read a whisper from across an ocean. This is where the universe offers a helping hand, turning its own architecture into a tool. Gravitational lensing does not just bend light, it concentrates it. A massive galaxy cluster in the foreground acts as a natural telescope, its gravitational curvature gathering the faint rays from a background object and funneling more of them toward us. The technical term is magnification, but the effect is pure revelation. A cluster can amplify the light of a single, distant galaxy by a factor of 10, 50, or even 100 times. This is not an incremental improvement, it is a transformational leap. It allows our human-built observatories to see galaxies that should be, by all rights, forever invisible. We are borrowing the universe's own lens to peer deeper into its past than we ever could alone. Take the galaxy cluster known as MACSJ 0717. To our telescopes, it is a chaotic city of galaxies, a dense knot of light, but astronomers looking through it saw something else. In its warped background, they found not just one or two magnified galaxies, but a whole population of them stretched into faint blue arcs. These are not nearby objects, they are glimpses of the cosmic dawn, galaxies seen as they were when the universe was only a fraction of its current age. Without the cluster's magnifying power, these infant galaxies would be mere specks of noise, lost in the black. With it, we can study their shapes, their rates of star formation, and begin to understand how the first structures in the universe assembled themselves. This natural telescope has no moving parts, it requires no funding, and it operates on principles written into the fabric of reality. It gives us a direct line of sight to eras we could otherwise only theorize about. But magnification is only one half of the gift. This cosmic lens does more than just make faint things brighter, it also makes hidden things visible. That missing mass became the central mystery. When astronomers carefully weighed these cosmic lenses, they found a startling discrepancy. By measuring the severity of the distortions, how sharply the background galaxies were stretched into arcs and rings, they could calculate the total mass of the foreground cluster causing the lens. It is a direct cosmic scale reading gravity's signature. The answer they got never matched the mass they could see. The luminous stars, the glowing clouds of gas, all the ordinary matter that shines, it accounted for only a small fraction, perhaps 10 or 20%, of the gravitational pull they were measuring. The scale was telling them something profound. The majority of the mass in the universe does not glow. It does not emit light, absorb light, or reflect light in any way we can detect. It is simply there, an invisible scaffolding shaping everything we see. We call this missing component dark matter. Gravitational lensing did not just suggest its existence, it provided the first way to map its shape. Think of it like this: you are looking at a clear, calm pond on a windy day. You see the ripples and distortions on the water's surface, but you cannot see the wind itself. By carefully charting the patterns of those ripples, you can deduce the wind's direction and strength. In the same way, by charting the precise distortions of thousands of background galaxies, scientists can trace the invisible gravitational landscape of the dark matter halo surrounding a cluster. These maps are breathtaking. They show vast, diffuse clouds of dark matter, often stretching far beyond the visible galaxies, with dense knots and filaments connecting cosmic structures in a vast, unseen web. One of the most famous examples is the Bullet Cluster. Here, two galaxy clusters collided in what must have been one of the most energetic events since the Big Bang. During this collision, the clouds of hot gas from each cluster, the normal, visible matter, slammed into each other, slowed down, and got stuck in the middle. But the dark matter, which does not interact with anything except through gravity, sailed right through the collision. The lensing maps revealed the dark matter halos from each cluster, now separated from the visible gas, drifting ahead of it like ghostly shadows. This was a crucial piece of evidence. It showed that dark matter is not just a mathematical fix, but a real, physical substance that behaves differently from the ordinary matter we know. It is the hidden architecture of the cosmos, and gravitational lensing is the only tool we have that lets us trace its blueprint directly. We are literally drawing maps of the invisible. But what if the lens itself could move? What if we could watch the universe's magnifying glass drift across the sky, creating and distorting mirages in real time? This possibility leads us to one of the strangest and most useful predictions of all: the phenomenon of a supernova appearing in multiple places at once. The universe's grandest mirages are spectacular, but they are also rare. For every perfect Einstein ring, there are millions of distant galaxies whose light passes through a less dramatic but far more common kind of distortion. This is the frontier of weak lensing, where the signal is not a brilliant arc but a whisper, a statistical sigh written across the cosmos. To see it, you must look not at one galaxy, but at multitudes. Picture a vast field of distant, faint galaxies. If the universe were empty, their shapes would be randomly scattered like confetti, pointing in every direction. But the universe is not empty. Every thread of the cosmic web, every filament of dark matter, and every cluster of galaxies creates a tiny depression in spacetime. As the light from those background galaxies travels for billions of years to reach us, it passes through this uneven, invisible terrain. Each thread gives the light a barely perceptible nudge. The result is not a dramatic bending, but a subtle, coherent shearing. The galaxies appear ever so slightly stretched, not into arcs, but into aligned ellipses, as if a gentle cosmic tide has washed over them. This collective distortion is called cosmic shear. No single galaxy's distortion is trustworthy. It could simply be an oddly shaped galaxy. But by surveying millions of them across enormous swaths of the sky, a pattern emerges from the noise. It is the fingerprint of all the mass, seen and unseen, that lies between those galaxies and our telescopes. This is how we map the invisible. By measuring the precise amount and direction of this shear across different distances, astronomers can reconstruct a three-dimensional mass map of the large-scale structure of the universe. They are tracing the outlines of the cosmic web itself, charting the vast dark matter halos and the empty voids between them. This technique does more than just show us where the dark matter is. It tells us how the universe has grown over time. By comparing the shear patterns from galaxies at different distances, which means from different eras in cosmic history, we can watch the cosmic web assemble itself. We can see how gravity has pulled matter into clusters and filaments over billions of years, and here weak lensing reveals its most profound purpose. This growth history is exquisitely sensitive to the push of dark energy, the mysterious force causing the expansion of the universe to accelerate. Dark energy works against gravity's pull, suppressing the growth of cosmic structure. By precisely measuring how the cosmic shear signal changes across cosmic time, we are taking the universe's temperature. We are constraining the properties and strength of dark energy itself. It is a measurement of the fate of everything, gleaned from the faint, aligned stretches of light from countless galaxies. The story is no longer written in brilliant rings, but in a universe-wide signature of gentle, relentless tide. The most powerful telescopes in the universe were not built by human hands. They are the galaxy clusters, titanic cities of 1,000 galaxies bound together by gravity. Their collective mass is so immense, they warp the space around them into a natural, cosmic lens of staggering scale. Within the curved space surrounding a cluster like Abell 178, the rules of light are rewritten. A single, distant galaxy does not appear as a neat, spiral pinprick. Instead, its light is pulled and stretched as it navigates the cluster's gravitational terrain, smearing across the sky in brilliant, blue arcs of light. These are not galaxies as they are, but galaxies as the cluster's gravity forces us to see them, magnified and distorted into celestial apparitions. In the cluster Abell 370, one such background galaxy has been lensed into a spectacular, winding form astronomers nicknamed the Dragon. It is not a mythical creature, but a single galaxy torn into multiple, shimmering segments, its head, tail, and body stretched across space by the cluster's invisible hand. This is the gift of the cosmic lens. By studying the precise curvature of these giant arcs, we achieve two profound insights at once. First, we get an ultra-magnified view of the distant universe, seeing the intricate structures of galaxies so far away their light is a fossil from the cosmos's youth. Second, and perhaps more astonishingly, the arcs act as a diagnostic tool for the lens itself. The pattern of the distortions is a direct map of the cluster's total gravitational field. By reverse engineering the mirage, astronomers can deduce how the cluster's mass is distributed, untangling the complex interplay between the hot, glowing gas that fills the space between galaxies and the vast, invisible halo of dark matter that holds the entire structure together. We are using the distorted image of one galaxy to weigh and measure another, using light as a probe to see the unseen. The search for the universe's first lights pushes our technology to its absolute limit. We are trying to see the glow from the cosmic dawn, a time when the first stars and galaxies ignited out of a dark, primordial fog. This light has traveled for over 13 billion years, stretched and dimmed by the expanding universe into a faint infrared whisper. Even the colossal mirror of the James Webb Space Telescope strains to collect enough of these ancient photons. The solution, once again, lies in the universe's own design. Galaxy clusters like the one designated SMACS 0723 become more than just subjects of study. They become essential partners in our search. The first deep-field image from Webb showcased this cluster not for its own brilliant galaxies, but for what its gravity reveals behind it. The cluster's immense mass warps spacetime into a natural magnifying glass, focusing the faint light from galaxies far more distant. In that single, iconic image, the red, distorted smudges arcing around the cluster are not flaws or artifacts. They are magnified portraits of galaxies so young, the universe itself was only a few 100 million years old. Without the cluster's gravitational boost, these infant systems would be invisible, lost in the black. With it, they are brought into sharp enough focus that we can begin to ask profound questions. How big were these first galaxies? How quickly were they forging their first generations of stars? What were their shapes? The lensing magnification provides the crucial brightness we need to split their light into spectra, the cosmic fingerprints that reveal their composition and distance. We learn that some of these early galaxies are surprisingly massive and mature, forming stars at a ferocious rate even in the universe's infancy. This challenges our models of how cosmic structures assemble, suggesting the first seeds of galaxies may have formed earlier and grown faster than we ever thought possible. Each distorted red smudge is a portal, a chance to witness the universe writing its own opening chapters, using gravity itself to illuminate the very first pages. This cosmic tide, measured across billions of years, points toward a force even more mysterious than dark matter. The universe is not just expanding, it is accelerating, pushed apart by something we call dark energy. But how do you measure the push of an invisible force across the entire cosmos? Gravitational lensing offers a test of pure geometry, a way to trace the history of space itself. One of the most elegant methods uses a distant quasar, its light split into multiple mirages by a foreground galaxy. Each of those images is a snapshot of the same object, but the light for each one has traveled a different path through the warped spacetime around the lens. Some paths are longer, some are shorter. This means the light does not arrive at the same time. If the quasar flickers or changes brightness, that flicker will appear first in one image, then days, weeks, or even months later in another. Astronomers watch these cosmic echoes with extraordinary patience, monitoring the images for years to measure the precise delay between them. This time delay is not just a curiosity, it is a cosmic yardstick. It depends critically on the total distance the light has traveled, which is governed by how fast the universe has been expanding over its entire history. By carefully modeling the mass of the foreground lens and measuring these delays, scientists can calculate a fundamental number, the Hubble constant, which tells us the current rate of the universe's expansion. This is a completely independent check, a measurement built from the geometry of bent light and patience. Its value is crucial because other methods for measuring the expansion rate, like using distant supernova or the cosmic microwave background, have begun to show a persistent, puzzling tension. They do not quite agree. Time delay cosmography gives us a third way to read the cosmos, a new voice in the conversation that may help us understand if the discrepancy is a measurement glitch or a sign of entirely new physics. But it goes further. The precise value of the Hubble constant and how it has changed over time is exquisitely sensitive to the nature of dark energy itself. Is dark energy a constant force woven into the fabric of space, or is it something that evolves and changes? By using lensing to map the expansion history, we are probing the equation of state of this dominant, unseen driver of our cosmic fate. We are asking the universe through the delayed whispers of a flickering quasar what lies ahead. Among all the cosmic mirages, one stands out for its sheer elegance and symmetry. It is the Einstein ring, a perfect circle of light hanging in the void. This phenomenon occurs under the most precise cosmic alignment imaginable. A distant, brilliant source like a galaxy or a quasar must sit almost perfectly directly behind a massive foreground object, like another galaxy or a cluster. When this happens, the foreground mass bends the fabric of spacetime into a circular lens. The light from the background object, traveling from all sides of that source, gets warped equally in all directions as it passes around the lens. To our telescopes, the result is not a smeared arc or a double image, but a complete glowing halo encircling the foreground object. It is the universe's most perfect optical illusion, a ring of fire where no physical ring exists. The beauty of an Einstein ring is more than cosmic decoration, it is a gift of precision. Because the distortion is so symmetrical, the mathematics become beautifully clean. Astronomers can measure the ring's radius with extraordinary accuracy, and from that single measurement, they can calculate the total mass of the foreground object, causing the lensing with a confidence that other, messier distortions cannot provide. These rings have become celestial scales. They have been used to weigh distant, elliptical galaxies, confirming the vast halos of dark matter that surround them. They have even helped us probe objects within our own galaxy. In a remarkable event, astronomers observed a star in the Milky Way briefly magnify the light of a far more distant star. The precise, ring-like signature of that microlensing event revealed not just the foreground star, but a planet orbiting it, a world otherwise lost in its star's glare. Each perfect circle is therefore a laboratory. It confirms the deep geometry of spacetime, it measures the invisible, and it occasionally spotlights hidden worlds. They are reminders that in the chaos of the cosmos, moments of perfect alignment can create not just art, but profound understanding. While galaxy clusters bend the cosmos on a grand scale, gravitational lensing also operates in our own galactic neighborhood with a delicate, fleeting touch. This is the realm of microlensing, where the actors are not titanic clusters but single stars, and the lens itself is in motion. Imagine a solitary star drifting through the vast spaces between suns. By chance, from our vantage point on Earth, it passes directly in front of a much more distant star. For a brief window of time, the gravity of this foreground star warps the space around it, acting as a tiny magnifying glass. The light from the background star, normally a faint, steady point, brightens dramatically as the alignment peaks, then fades back to normal as the stars continue on their separate paths. This is a microlensing event, a transient flash in the galactic dark that can last for weeks or months. It is a one-time cosmic coincidence, impossible to predict and impossible to repeat, yet within its unique signal lies an extraordinary possibility. The true power of this method emerges when the foreground star is not alone. If it hosts a planet, that planet's own gravity adds a tiny, secondary distortion to the lens. As the planet moves through the alignment, it creates a distinct, sharp blip superimposed on the broader brightening curve of the host star. This secondary signal is the planet's fingerprint. What makes microlensing revolutionary is its unique sensitivity. Unlike the transit method, which requires a planet to pass directly between its star and us, or the radial velocity method, which relies on a star's wobble from a planet's gravitational tug, microlensing does not depend on the planet's orbit being edge-on or close in. It can detect planets orbiting at vast distances from their host star, in regions so cold and remote they were once thought barren. It has revealed gas giants in orbits resembling our own Jupiter's, but also something even stranger, a population of worlds so distant they may be barely gravitationally bound, or perhaps not bound at all. This technique has unveiled what astronomers call free-floating planets, dark worlds untethered to any sun, wandering the interstellar void. These are planets that may have been flung from their nascent systems by gravitational encounters, or perhaps formed in isolation from tiny clouds of gas and dust. They are invisible to every other search method, yet microlensing catches their ghostly signature as they drift silently in front of a distant background star, their own gravity creating a brief, lensing flash with no stellar host light to drown it out. Each detection adds a new, shadowy piece to the puzzle of planetary system architecture, suggesting that for every star-bound planet we see, there may be countless more of these nomads drifting in the dark. The story of planets is not just one of orderly orbits around a central fire, but also of ejection, solitude, and a colder, more solitary kind of existence. Microlensing listens for the whispers of these lost worlds, proving that even the smallest distortions in starlight can illuminate the deepest corners of our galaxy's untold stories. But our view of these cosmic mirages is not limited to the rainbow of visible light. Beyond the optical spectrum, a silent symphony plays out in the long, cool waves of radio. Radio telescopes peer into a different layer of reality, one where gravity's lens bends not just light, but the entire electromagnetic spectrum. Observatories like the Very Large Array and the Atacama Large Millimeter Array listen in on this hidden frequency band, transforming our understanding of lensed objects. A quasar that appears as a brilliant point of light in an optical image often reveals its true, violent nature in radio waves. These observatories can map the colossal jets of superheated plasma screaming away from the quasar's central black hole, structures that can stretch for thousands of light years. When such a quasar is gravitationally lensed, its radio emissions are bent and multiplied just like its light. This gives us multiple, magnified views of these intricate jet systems from slightly different angles, allowing astronomers to reconstruct their three-dimensional structure in a way that would be impossible with a single direct image. We can study how these jets interact with their host galaxy and the intergalactic medium, physics that is often obscured in optical observations. Furthermore, radio waves pierce through cosmic dust that blocks visible light. This allows arrays like ALMA to study the cold, dense clouds of gas and dust in lensed galaxies from the early universe, the very raw material from which stars are born. By analyzing the radio signatures of molecules like carbon monoxide in these magnified galaxies, we can measure their gas content, temperature, and dynamics, painting a complete picture of how the first galaxies fueled their stellar factories. The technique of radio interferometry, which combines signals from multiple dishes to act as one giant telescope, provides another crucial advantage: sheer precision. The detailed radio maps of a lensed system can be exquisitely sharp, revealing fine structures within the distorted arcs. This precision acts as a powerful constraint for astronomers building mass models of the foreground lensing cluster. It is like having a higher resolution grid on our cosmic map, allowing us to pinpoint the distribution of dark matter with even greater accuracy. Each frequency of light tells a different part of the story, and by listening to the radio whispers from these gravitational mirages, we hear the universe's most energetic processes and its coldest, quietest beginnings, all through the same curved window of spacetime. The intricate dance of light and gravity we observe is not a simple puzzle to solve. Decoding these cosmic mirages requires a tool of almost equal scale to the universe itself. To make sense of the vast statistical whispers of weak lensing or the precise distortions of a giant arc, astronomers turn to a digital cosmos. They build entire universes inside supercomputers. These are not video games, but rigorous mathematical models, virtual laboratories where the laws of physics as we understand them are set in motion from the first moments after the Big Bang. The simulations begin with a smooth, nearly uniform sea of dark matter, seeded with tiny fluctuations drawn from the cosmic microwave background. Then they press play. Over billions of simulated years, gravity takes over. dark matter clumps into halos which merge and grow, tracing out the vast filaments and voids of the cosmic web. Into these dark matter scaffolds, the complex physics of gas, star formation, and supermassive black holes is woven, giving birth to virtual galaxies that populate the virtual halos. The result is a synthetic universe, a digital twin born from our best cosmological theories. But the real test comes next. The scientists take the perspective of a virtual observer within this simulation. They simulate the journey of light from billions of distant, synthetic galaxies, letting it travel through the warped spacetime of all the virtual dark matter and galaxies in its path. They calculate the subtle shearing, the dramatic arcs, all the lensing effects that would appear in their simulated telescope. This process generates a predicted map of cosmic distortions, a forecast of what the sky should look like if our models are correct. Then comes the critical comparison. They hold this simulated lensing map up against the real one, painstakingly compiled from surveys like the Dark Energy Survey, which has catalogued the shapes of hundreds of millions of galaxies. Do the patterns match? Does the statistical distribution of sheared galaxies in the real data align with the prediction from the virtual universe? If they align, it is a powerful vote of confidence for our entire cosmological framework, for our understanding of dark matter and dark energy. If they diverge, the discrepancy becomes a treasure map. It points directly to where our models are incomplete or wrong. Perhaps dark matter interacts with itself in ways we have not accounted for. Maybe the influence of dark energy changes over time in a different manner, or our understanding of how galaxies form within dark matter halos needs revision. Each mismatch is not a failure, but a guidepost steering theorists toward a more complete picture of cosmic evolution. In this way, supercomputer simulations act as the essential translator, turning the raw, beautiful chaos of bent starlight into precise cosmological insight. They are the bridge between what we see and what must be. But these cosmic whispers are not always easy to hear. The faint signal of a lensed galaxy is buried in a sea of noise, and teasing out the truth requires a kind of cosmic detective work that goes far beyond simply taking a picture. One of the most fundamental challenges is a simple question of identity. When we see a distant galaxy that appears slightly stretched, how do we know that stretch is from gravitational lensing and not just the galaxy's natural, intrinsic shape? Galaxies are not perfect spheres. They come as spirals, ellipticals, and irregular blobs. If we mistake a naturally oval galaxy for one that has been lensed, we corrupt the entire map. To solve this, astronomers rely on the law of large numbers. They survey not dozens, but hundreds of millions of galaxies. They assume that, on average, the universe has no preferred direction. So the intrinsic shapes of all those galaxies should point every which way, a random confetti of orientations. The weak lensing signal is the tiny, coherent pattern that emerges when you average all those shapes together, the subtle tide that makes the confetti drift ever so slightly in one direction. Isolating that drift means understanding and subtracting every other possible influence that could mimic it. The atmosphere itself is a constant adversary for ground-based telescopes. The churning air blurs starlight, an effect we see as twinkling, which can artificially smear a galaxy's shape. Even space-based telescopes are not perfect. Their optics can have tiny, built-in distortions that stretch images in predictable ways. Then there is the cosmic haze, interstellar dust within our own Milky Way that can redden and dim the light from distant galaxies, altering how we measure their brightness and size. Each of these effects is a systematic error, a bias woven into the data that has nothing to do with gravity. Left uncorrected, they would paint a false picture of the dark matter web. So astronomers become master calibrators. They use dense star fields to map the exact pattern of atmospheric distortion on a given night. They image known, unchanging star clusters to characterize every quirk of their telescope's optics. They create intricate models of the Milky Way's dust to correct for its dimming veil. The data is scrubbed, tested, and validated through a gauntlet of checks. This painstaking process is not glamorous, but it is the bedrock of the entire endeavor. The ultimate goal is to measure the cosmic shear, that universe-wide tidal signal, with such pristine accuracy that we can use it to weigh the most elusive forces in existence. A tiny residual bias could mistakenly point toward one model of dark energy over another, or suggest a modification to Einstein's gravity itself. The search for truth in the bent light of the cosmos is therefore a relentless pursuit of purity, a fight against noise to hear the universe's faintest sigh with perfect clarity. This meticulous work of cosmic cartography is about to receive an unprecedented upgrade. We stand on the brink of a new era in observational astronomy, one that will transform gravitational lensing from a specialized tool into a universal probe. A suite of next-generation observatories, both on the ground and in space, is poised to open the floodgates, delivering a torrent of data that will redefine our map of the invisible universe. The scale of what is coming is almost incomprehensible. Leading this charge from the mountains of Chile is the Vera Rubin Observatory. Its mission is called the Legacy Survey of Space and Time, and its ambition is breathtaking. Night after night for an entire decade, its enormous mirror and giant camera will scan the entire southern sky, not once, but over and over again. It will not just take pictures, it will make a movie of the cosmos. In that film, it will detect and measure the shapes of billions of galaxies. It will catch the fleeting flashes of millions of transient events, from supernova to the subtle brightenings of microlensing stars and planets. For weak lensing studies, this is a revolution. Instead of mapping millions of galaxies, we will map billions. The statistical noise that has limited our precision will be washed away by an ocean of data, revealing the dark matter web in sharper detail than ever before. But the view from the ground, even at a superb site, has limits. That is why we are also launching new eyes above the atmosphere. The Nancy Grace Roman Space Telescope, named for NASA's first chief astronomer, will peer even deeper. From its vantage point in space, free from the blurring of Earth's air, it will capture ultra-deep fields with exquisitely sharp image quality. This crystal-clear vision is perfect for measuring the most subtle distortions of weak lensing, allowing us to trace the cosmic web back to even earlier times with incredible fidelity. And then there is Euclid, a mission from the European Space Agency designed with a single, profound purpose. Euclid is an architect sent to map the geometry of the dark universe. It will meticulously measure the shapes and distances of over 1 billion galaxies, constructing the most precise three-dimensional map of cosmic structure ever made, using gravitational lensing as its primary tool. Together, these projects represent a coordinated assault on the unknown. They will generate not gigabytes but petabytes of data, a volume of information that would take thousands of years to view on a home computer. Within this digital universe, every strange arc, every statistical whisper of Shear, and every delayed quasar echo will be catalogued and analyzed on an industrial scale. We will move from studying individual cosmic lenses to understanding the population statistics of lensing across the entire sky. This will let us answer questions we can only ask now. How common are Einstein rings? What is the full population of free-floating planets? How exactly has the cosmic web evolved over the last 10 billion years? The answers will tighten the constraints on dark energy and dark matter, potentially revealing if our current models hold, or if we need to rewrite the textbooks on cosmic evolution. We are building a census of the hidden cosmos, and the first results are just over the horizon. The lens of gravity bends more than just the path of light. It warps the very fabric of reality, and that means its influence extends to a far more elusive cosmic messenger, gravitational waves. When two of the universe's most extreme objects, like black holes or neutron stars, spiral together and finally merge, they do not just produce a flash of light. They shake the foundations of spacetime, sending out ripples that travel at the speed of light across the cosmos. These are gravitational waves, a direct echo of the most violent events in the universe. And just like starlight, these ripples must travel through the cosmic landscape. If their journey takes them through the warped spacetime surrounding a massive galaxy cluster or a supermassive black hole, something extraordinary can happen. The gravitational waves themselves can be gravitationally lensed. The cluster's immense gravity would bend the path of the ripples, potentially splitting the single signal into multiple copies, each taking a slightly different route around the cosmic lens. Our detectors here on Earth would then sense the same cataclysmic merger event not once, but 2 or more times, with each echo arriving hours, days, or even weeks apart. This has not been observed yet, but the search is on. A future detection of a lensed gravitational wave would be a discovery of monumental importance. It would offer a completely new kind of ruler for the cosmos. By measuring the time delay between the multiple echoes of the same merger, scientists could calculate distances across the universe in a way that is entirely independent of light. It would be a pure test of spacetime geometry, free from the complications of dust, gas, or the chemical makeup of stars. This independent measurement could help resolve the persistent tension in measurements of the universe's expansion rate, potentially revealing if we are missing a fundamental piece of physics. More profoundly, it would fuse 2 of the most revolutionary fields in modern astronomy, gravitational wave detection and gravitational lensing, into a single, unified tool. We would no longer just be listening to the echoes of cosmic collisions. We would be using the universe's own lenses to magnify and multiply those whispers, opening a brand new window onto the dark, warped architecture of everything. Gravitational lensing is more than a tool. It is a philosophical statement written in light. This phenomenon forces us to confront a humbling truth about our place in the cosmos. We are inferring the architecture of reality from its shadows. The majestic rings, the statistical shears, the delayed echoes, all of them point toward entities we may never touch or see in any conventional way. Dark matter and dark energy are not things we have in a jar. They are conclusions written in the geometry of bent spacetime. Our entire understanding of the universe's composition, its past and its fate, rests upon this act of profound interpretation. We are like listeners in a dark room, hearing an echo and from its delay and distortion, drawing a precise map of the unseen chamber that created it. This shifts the very meaning of observation. For centuries, astronomy meant collecting light from distant objects. Now, it means decoding the distortions in that light to reveal the invisible masses that bent it along the way. We are not just looking at the universe, we are reading its hidden grammar. The cosmos operates on layers, with the most familiar one, the stars and galaxies we see, being only a luminous surface. Beneath it lies a vast, dark scaffolding that shapes everything. Gravitational lensing is our only direct line into that hidden layer. It proves that what is real extends far beyond what is visible. This is a powerful metaphor for the scientific process itself. Discovery is rarely about stumbling upon a glowing object in a dark room. More often, it is about noticing a subtle inconsistency, a pattern in the noise, a shadow that does not quite match the shape of the known. It is about having the courage to say that the best explanation for the strange bend in the starlight is an entire universe of unseen matter. Every arc of light is therefore a question and an answer about the nature of reality. It tells us that the universe is richer, stranger, and more hidden than our senses alone could ever perceive, and that true understanding comes from learning to see with the mind, using the laws of physics as our guide. A supernova is the final, brilliant signature of a dying star, a cosmic event so powerful it can outshine an entire galaxy. Yet even this staggering release of energy can be bent and multiplied by gravity's lens. In the distant galaxy cluster MACSJ 1149, astronomers were studying the intricate arcs of a lensed background galaxy when they noticed something new. A single, brilliant point of light had appeared within one of the magnified arcs. They named it supernova Refsdal. What made this discovery extraordinary was not just the supernova itself, but the cosmic stage on which it was playing out. The background galaxy hosting the supernova was being lensed by the massive foreground cluster into multiple, distinct images. These were not images of the galaxy at one moment in time, but images arriving along different, warped paths through spacetime. The light for each path had a different travel time. This meant the brilliant flash of the supernova should not appear just once, but multiple times, popping up in the other lensed images of the same galaxy like echoes in a cosmic canyon. Using detailed maps of the cluster's mass distribution, astronomers made a bold prediction. They calculated that the supernova's light had already arrived along one of the shortest paths, creating the initial flash they saw in 2014. But they forecast that another image of the same explosion, traveling a longer route, would arrive at Earth approximately 1 year later. They pointed the Hubble Space Telescope back at the cluster, and in December 2015, the prediction came true. A new point of light ignited exactly where their models said it would. This was not a different star, it was the same cataclysmic death seen again. The detection of the Refsdal supernova's reappearance was a landmark moment. It was the first time a lensed supernova had been predicted and then observed, a stunning real-world validation of our ability to map the invisible mass of galaxy clusters with precision. But more than that, it was a direct measurement of the universe's geometry. The time delay between the two appearances, over 360 days, acted as a cosmic stopwatch. It directly measured the difference in the length of the two light paths caused by the warped spacetime around the cluster. This single observation provided a unique, independent check on the cluster's mass and the expansion rate of the universe itself. We were not just watching a star die, we were witnessing a demonstration of spacetime as a tangible, flexible medium, where light from a single event could be split and delayed, offering us multiple glimpses of the same moment from the deep past. It was a form of observational time travel made possible by the patient, predictable curvature of the cosmos. The ultimate identity of dark matter remains one of cosmology's greatest puzzles, but among the many theoretical candidates, one stands out for its sheer, elegant simplicity. What if the invisible mass shaping galaxies is not an exotic new particle, but something we already know exists, born in the universe's violent first moments? These would be primordial black holes, not formed from collapsing stars, but from the intense density fluctuations in the searing hot soup of the early cosmos, potentially within its first fraction of a second. They could range in mass from smaller than an asteroid to larger than a star, drifting through space as dark, ancient relics. If they exist in vast numbers, they could account for some or even all of the dark matter. The challenge is proving it, for a black hole that does not actively feed is the perfect cosmic hide-and-seek champion. It emits no light, reflects nothing, and reveals its presence only through gravity. This is where the universe's magnifying glass offers our best chance at a sighting. Gravitational microlensing provides the perfect hunt. If a primordial black hole, a compact object of pure mass, were to drift silently across our line of sight to a distant star, its gravity would warp spacetime around it. For a period of days, weeks, or months, depending on its mass and speed, it would act as a natural lens, briefly magnifying the star's light before the alignment passed and the star returned to its normal brightness. The signature would be clean and unambiguous, a symmetric brightening and fading caused by an object with no light of its own. To conduct this search, astronomers have turned the Milky Way into a vast detector. Projects like the Optical Gravitational Lensing Experiment, known as OGLE, and the Microlensing Observations in Astrophysics, or MOA, continuously monitor hundreds of millions of stars toward the dense stellar fields of our galaxy's central bulge and our neighboring dwarf galaxies, the Magellanic Clouds. Their cameras stare patiently, night after night, compiling a cosmic movie, watching for the telltale flicker among the constant pinpricks of light. The data from these events is a treasure trove. The duration of the brightening event is a key clue, as a more massive lens will bend light over a wider region of space, creating a longer-lasting magnification as it moves. The precise shape of the light curve, the graph of brightness over time, can reveal subtle details, like whether the lens is truly a solitary object or if it might have a companion. After decades of searching, the results are profoundly revealing, yet still mysterious. While thousands of microlensing events have been catalogued, the vast majority can be explained by ordinary, faint stars, brown dwarfs, or planets. No event has yet provided the definitive fingerprint of a primordial black hole, but this absence of proof is itself a powerful form of knowledge. Each non-detection places a tighter constraint on the possible population. We can now say with growing confidence that primordial black holes cannot make up 100% of the dark matter, at least not across a wide range of masses. They could, however, still be a component, hiding in mass ranges that are harder to probe or constituting a smaller fraction of the cosmic budget. The hunt continues. A silent, statistical vigil in the data streams from telescopes around the world. Each unexplained light curve a potential window into the universe's first second and the true nature of the shadow that holds the light together. Even our own star participates in this cosmic dance of light. The Sun, a modest mass by galactic standards, still warps the space around it enough to bend the starlight from distant suns. This subtle deflection was the first great test of Einstein's theory. In May of 1919, two teams of astronomers led by Arthur Eddington journeyed to opposite sides of the globe, to Brazil and the island of Principe, to observe a total solar eclipse. With the moon's disk blocking the sun's blinding face, the stars around it became visible in the daytime. The teams carefully photographed those stars and compared their positions to images taken of the same patch of sky at night, months earlier. The result was a tiny but measurable shift, exactly as Einstein had predicted. Starlight passing near the sun was not traveling in a straight line, it was curving along the sun's gravitational well. That single observation, announced later that year, catapulted Einstein to global fame and transformed our understanding of gravity from a mysterious force into a property of curved space. It was the first concrete proof that the universe truly operates by the rules of general relativity, and it all hinged on the sun acting as a gravitational lens. Today, that same principle inspires a vision that stretches the imagination to its limits. Scientists have proposed an audacious mission, not to use a telescope to look at the sun, but to use the sun itself as the telescope. The concept is based on a simple yet profound extension of the lensing effect. Just as a galaxy cluster has a focal line where light from a distant source is brought to a point, so does our sun. That gravitational focus is not a single point, but a line extending outward from about 550 astronomical units, a staggering distance where 1 astronomical unit is the average distance from Earth to the Sun. To reach this region, a probe would need to travel over 13 times farther than Pluto. If we could someday send a spacecraft with a modest telescope to that precise line and aim it back toward a specific exoplanet, something miraculous would happen. The sun's gravity would bend the faint light from that distant world, focusing it into a brilliant, magnified ring around the solar disk. Our probe's telescope would be positioned inside that ring, collecting the focused light. The potential is staggering. Instead of seeing an exoplanet as a single, blurry pixel, such a solar gravitational lens could, in theory, resolve its surface in extraordinary detail. We could map continents and oceans on a world light years away, search for signs of vegetation, or even detect the lights of cities. The technical challenges are, of course, monumental. The journey would take decades with current propulsion, and the precision required to align with a target light years away is almost unimaginable. Yet, this is not mere science fiction. It is a direct consequence of the physics we have already confirmed. It represents the ultimate expression of using gravity as a tool, from a humble measurement during an eclipse to a blueprint for seeing alien worlds. The same principle connects them, proving that the most powerful lenses in the universe are not made of glass, but of spacetime itself. Gravity is the universe's greatest artist, and its canvas is light itself. The images beamed back by observatories like Hubble and the James Webb Space Telescope are more than data points, they are visual symphonies. A distant galaxy stretched into a shimmering blue arc, a perfect golden ring of fire encircling a dark void, a cluster of stars smeared into celestial brushstrokes across the black. These are not illustrations or artistic renderings. They are real photographs of the cosmos captured through a lens of pure spacetime. This aesthetic power is not a secondary effect. It is a primary force in how we understand our place in the universe. For scientists, these warped shapes are precise mathematical equations made visible, a map of invisible mass, but for the public, they are a direct line to wonder. They transform an abstract concept like the curvature of four-dimensional spacetime into something you can feel in your gut. You do not need to understand the tensor calculus of general relativity to be moved by the sight of an Einstein ring. Its perfect symmetry speaks a universal language of order emerging from chaos, a cosmic magic trick revealed. This visual bridge is perhaps the most powerful tool for science communication we have ever had. A complex paper on dark matter halos might reach a few hundred specialists, but an image of a galaxy cluster warping the light of 1,000 distant suns can captivate millions. It makes the invisible tangible. It allows anyone to look at those delicate arcs and intuitively grasp that there is something massive there, bending the light, even if that something cannot be seen. The image does the explaining. It invites questions, sparks curiosity, and makes the distant, impersonal cosmos feel intimately strange and beautiful. In this way, these photographs serve a dual purpose. They are rigorous scientific instruments, and they are modern celestial art. They are painted not by human hands, but by the fundamental forces that sculpt reality. When we share them, we are not just sharing discoveries, we are sharing an experience. We are reminding everyone that the pursuit of knowledge is not a cold, clinical process. It is a deeply human endeavor, driven by the same awe that our ancestors felt looking up at the starry sky. It is emotional, it is aesthetic, it connects the logic of mathematics to the poetry of existence. Every warped galaxy is a reminder that the universe is not only knowable, but also breathtakingly beautiful, and that sometimes the deepest truths are revealed not in numbers alone, but in the light bent into impossible, glorious shapes. These cosmic mirages emerge from a geometry that defies our everyday intuition. How do you explain the bending of light by an invisible force, or the warping of space itself? To build that conceptual bridge, scientists and educators turn to simple, physical models that translate abstract mathematics into something we can see and touch. One of the most enduring is the rubber sheet analogy. Picture a large, taut sheet of stretchy fabric held flat. This represents empty, flat spacetime. Now place a heavy bowling ball in the center. The ball's weight creates a deep depression in the sheet, curving the fabric around it. This is a massive object like a star or galaxy, warping the spacetime around it. If you then roll a small marble representing a particle of light across the sheet, its path will no longer be a straight line. As it nears the depression, it will curve inward, following the contours of the curved fabric before rolling away. The marble is not being pulled by a mysterious force. It is simply following the shortest path along a bent landscape. This visual makes a profound idea tangible. Mass tells spacetime how to curve, and curved spacetime tells light how to move. Another powerful analogy sits right on your dinner table. Place a wine glass on a checkered tablecloth and look through its base. The straight lines of the grid pattern will appear bent and circular around the stem. The glass acts as a lens, distorting the image of the objects behind it. In this case, the glass is the massive object, the tablecloth represents the fabric of spacetime, and the distorted grid lines are the bent paths of light from a distant source. These analogies are not perfect, of course. The rubber sheet uses gravity to explain gravity, and the wine glass is a material object, not an invisible field. But their power lies not in perfect accuracy, but in providing a crucial first step. They give our minds a foothold, a way to visualize a four-dimensional concept in a three-dimensional world. They transform the alien idea of warped spacetime into a story about landscapes and lenses, a story where light is not magically bent, but is simply being a faithful traveler, following the shape of the road the universe has built for it. The light from a distant galaxy, stretched and magnified, becomes more than a mirage. It becomes a microscope. When a foreground cluster acts as a cosmic lens, it does not merely make a faint galaxy brighter, it effectively brings it closer. The magnification can be so powerful that details which would otherwise be a single, unresolved pixel in our telescopes are blown up into a sprawling, intricate map. We are granted a close-up view of a galaxy's inner workings, a privilege normally reserved only for the very nearest galaxies to our own. This transforms lensing from a tool for discovery into a tool for dissection, allowing us to study the anatomy of cosmic evolution in real time. Within a highly magnified, lensed galaxy, astronomers can do something extraordinary. They can chart where new stars are being born. Regions of intense star formation glow with a specific signature in ultraviolet and infrared light, and with the resolution provided by the gravitational lens, these stellar nurseries can be pinpointed. We can see if they are scattered across the galactic disk or concentrated in a furious central burst. Simultaneously, by observing at different wavelengths, we can map the cold, dark clouds of dust and gas, the raw material from which those stars condense. This lets us see the direct relationship between the fuel and the fire. Does the gas distribution dictate where stars ignite, or do the explosions of the first stars blow the gas away, shutting down further formation nearby? In a lensed galaxy, we can watch this feedback loop in action. This detailed view provides a crucial reality check for our theories. For decades, astrophysicists have used supercomputers to simulate how galaxies form and grow over billions of years. These virtual universes make predictions about how gas should cool, how stars should cluster, and how the overall structure of a galaxy should emerge from the primordial darkness. But a simulation is only as good as its test. A lensed galaxy from the early universe offers that test. By comparing the intricate maps of gas, dust, and star formation from a real, magnified galaxy to the predictions of the simulations, scientists can see where their models succeed and where they fail. Perhaps the simulated galaxies form stars too quickly, or maybe their gas is distributed too smoothly. Each mismatch is a clue guiding theorists to refine the complex physics of supernova winds, black hole activity, and dark matter interactions that shape a galaxy's life. The gift of this magnification is a window into a lost era. The processes that built the first galaxies were violent and rapid, dominated by frantic star formation and frequent mergers. In our nearby modern universe, such ferocious activity is rare. Most galaxies, including our Milky Way, are relatively settled and mature. Studying a nearby galaxy to understand the early universe is like studying a calm, elderly adult to understand the tumultuous experiences of their childhood. You might see the lasting effects, but you miss the dynamic action. A strongly lensed galaxy, often observed as it was 8 or 10 billion years ago, captures that childhood in progress. We see the chaos and the creativity of youth, the period when the most fundamental traits of a galaxy were being forged. This close-up view of the past is our only direct way to understand why galaxies look the way they do today, revealing the ancient events written into the spiral arms and glowing cores of every island universe we see. This intricate cosmic detective work begins with a simple, profound inversion. We see the distorted image, the warped arcs and multiple mirages, and we must work backwards to uncover the hidden mass that caused it. This process is called mass reconstruction, and it is how we transform a beautiful illusion into a precise map of the invisible. Astronomers start by building a digital model of the foreground lens, whether it is a single galaxy or an immense cluster. This model is not a guess, it is a sophisticated hypothesis built from our understanding of cosmic architecture. It incorporates several key components. First, there is the dominant, unseen player, a smooth, diffuse halo of dark matter, which provides the bulk of the gravitational pull. Superimposed on this are the individual member galaxies, each with its own smaller dark matter halo and visible stars. And finally, there is the hot, X-ray emitting gas that fills the space between the galaxies, adding its own mass to the equation. This parameterized model is essentially a mathematical description of the lens's gravity well. The next step is where the computation begins. Scientists feed this model into powerful software and ask it a question. Given this specific arrangement of mass, how would it distort the light from a known background galaxy? The software traces millions of simulated light rays through the warped spacetime of the model, predicting where and how the background object should appear to us, whether as a ring, an arc, or multiple smeared images. The initial prediction almost never matches the real observation perfectly. So begins an iterative dance of adjustment. Using statistical techniques like Bayesian inference, the model's parameters are tweaked. The dark matter halo is made slightly more concentrated here. The mass of a central galaxy is adjusted there, and the calculation is run again. The goal is to minimize the difference between the predicted mirage and the actual one captured by the telescope. It is a gradual refinement, a digital sculpture of the unseen, carved by the light it bends. After hundreds or thousands of these iterations, the model converges on a solution, a mass map that best explains the observed distortions. The result is nothing short of revelation. We see a contour map of gravity itself, with dense knots of mass corresponding to the visible galaxies, embedded within a vast, sprawling sea of dark matter that often extends far beyond the cluster's luminous edge. These reconstructions are our most direct evidence for the dark matter scaffolding. They show us that what we see with our eyes, the brilliant cities of stars, are merely the decorative lights strung along an invisible framework, a framework we can only trace by patiently decoding the universe's bent starlight. Yet for all its power, this cosmic lens has its own inherent limits. It reveals a universe of shadows, but not the substance of the shadow itself. Gravitational lensing is a geometric tool, a master of mapping the shape and weight of the invisible, but it remains silent on the deepest question of all: what is the hidden mass actually made of? The distortions confirm that dark matter exists and show us precisely where it is, but they cannot tell us if it is a sea of exotic particles, a population of ancient black holes, or something even more strange. The map is not the territory. It tells us the landscape of gravity, but not the material that forms the hills and valleys. This is the fundamental boundary of the technique. It measures the effect, not the cause. The lensing patterns are a spectacular signature of missing mass, but the identity of that mass must be hunted by other means, in particle accelerators deep underground or in the subtle signals of the cosmic microwave background. Lensing points the way, but it cannot open the box. Beyond this, the interpretation of every warped arc and sheared galaxy is built upon a foundation of assumptions. Astronomers must construct a model of the lens, a mathematical description of how its mass is distributed, to decode the mirage. But here, a challenge arises. Different arrangements of mass can sometimes produce eerily similar patterns of bent light. This is known as a degeneracy. Imagine trying to deduce the shape of a hidden object by only studying its shadow on a wall. A sphere and a cube held at just the right angle can cast an identical circular shadow. In the cosmos, a compact, dense knot of dark matter and a more extended, diffuse halo might, under certain alignments, bend the light from a background galaxy in nearly the same way. Untangling this requires additional clues, like measuring the hot X-ray gas in a cluster or observing the motions of the galaxies within it, to break the degeneracy and arrive at the most likely truth. The tool is powerful, but it is not infallible, and its answers are always probabilistic, a best fit to the light we see. Finally, gravitational lensing is not a tool we can point at will. We are at the mercy of cosmic geometry. To see a strong lens, we need a near-perfect alignment between a distant light source, a massive foreground object, and our telescope. Nature must provide the lens for us. This means we can only study the specific slices of the universe where this rare alignment happens to occur. We cannot choose to map the dark matter around any random galaxy, only the ones that conveniently line up with something bright behind them. Our view is selective, a series of brilliant but isolated flashlights pointed into the dark, rather than a uniform floodlight illuminating the whole cosmic web. These limitations are not failures, they are the defining edges of the tool, reminding us that every window into the cosmos offers a specific kind of view, and true understanding comes from combining them all. The story of bent light began not with a telescope, but with a question about an apple. For centuries, Sir Isaac Newton's law of universal gravitation reigned supreme, describing a universe where massive objects exerted an invisible pull across space. Within this framework, some thinkers pondered the nature of light itself, which Newton imagined as a stream of tiny particles or corpuscles. If light was made of material particles, they reasoned, then surely it too should feel gravity's tug. A beam of starlight grazing the sun would be pulled slightly toward it, its path deflected by a minuscule, almost imperceptible amount. This was a logical guess born from the physics of its time. Yet it was incomplete, a hint of a deeper truth waiting to be uncovered. The puzzle intensified with Einstein's own special theory of relativity, which established the speed of light as the universe's ultimate constant, an unwavering cosmic speed limit. This created a profound tension with Newton's idea of gravity as an instantaneous force. How could light, moving at this fixed, maximum speed, be affected by a force that supposedly acted across space in a flash? Einstein spent a decade wrestling with this contradiction. His breakthrough was one of the most beautiful leaps in human thought. He realized gravity was not a force at all, but a consequence of geometry. Massive objects did not pull on light, they warped the very stage upon which light traveled. Space and time were fused into a flexible fabric, spacetime, and the presence of mass or energy curved that fabric. Light, always following the shortest path, simply traveled along this new, curved landscape. This geometric view of gravity, his general theory of relativity, made a precise prediction. The deflection of starlight by the sun would be exactly twice the value calculated under Newton's old corpuscle theory. The difference was small, but it was measurable. The universe provided the perfect experiment during a total solar eclipse, when the moon's shadow would blot out the sun's glare, allowing astronomers to see the stars positioned right beside it. In May of 1919, two expeditions led by Arthur Eddington journeyed to opposite sides of the globe to capture this critical moment. Their photographs, compared against images of the same star field taken months earlier, revealed the telltale shift. The starlight had bent, and by the amount Einstein's new geometry demanded. The announcement made headlines worldwide, transforming a theoretical physicist into a global icon almost overnight. That single observation did more than validate a theory. It fundamentally changed our conception of reality. We moved from a universe of forces acting across void to a universe of dynamic, warped geometry. The tiny deflection of starlight was the first crack in the classical worldview, a crack that would widen into the doorway we now use to see the invisible cosmos. That journey from Newton's speculative particles to Eddington's confirming photographs reminds us that our greatest discoveries often begin not with new data, but with the courage to reimagine the very fabric of the world we think we know. But how do we know how far away any of these mirages truly are? Measuring distance in the cosmos is not a single act, but a careful, step-by-step ascent, a cosmic distance ladder. Each rung of this ladder depends on the one below it. We start with simple geometry to measure distances within our solar system, then use those to calibrate the brightness of certain pulsating stars in our galaxy, which then help us gauge the distance to nearby galaxies containing a special kind of exploding star, a supernova. It is a chain of inference, and a single misstep on a lower rung can throw off the measurements for the entire observable universe. This is where the pure geometry of gravitational lensing offers a revolutionary alternative. By measuring the time delay between multiple images of a flickering quasar, we can calculate a direct, absolute distance that does not depend on any other rung of the traditional ladder. The method relies on just three things: the geometry of the lens, the speed of light, and the patience to wait for the cosmic echo. Because it is independent, it acts as a crucial cross-check. It is like having two completely different maps to the same destination, one drawn by following landmarks, and the other by using a compass and a precise measurement of your walking speed. If they agree, our confidence soars. If they disagree, it signals a hidden turn we might have missed. This independent rung is now helping to resolve one of the most significant tensions in modern cosmology: the precise value of the Hubble constant, the number that tells us how fast the universe is expanding today. Measurements based on the cosmic microwave background, the afterglow of the Big Bang, suggest one value. Measurements using supernova and other traditional rungs of the distance ladder suggest a slightly faster expansion rate. They disagree by just a small but stubborn amount. Time delay cosmography, the technique born from lensed quasars, provides a third, purely geometric voice in this debate. Its early results are leaning toward the faster expansion rate hinted at by the supernova. This is not just about settling an argument over a number. It is a potential clue that our standard model of cosmology, while incredibly successful, might be missing a subtle ingredient. Perhaps dark energy is not constant but changing over time. Maybe neutrinos are more massive than we thought. Or there could be another, unknown factor influencing the expansion history of the cosmos. Each precise time delay measurement is like a new survey point on that map, tightening the constraints and guiding us toward a deeper understanding of why the numbers do not quite align. In this way, the warped light from a distant quasar does more than create a mirage. It becomes a fundamental benchmark, a fixed point in the expanding void against which we can measure the growth and fate of everything. This vast new map of the cosmos will not be drawn by a single hand. The Vera Rubin Observatory, the Roman Space Telescope, and Euclid are not just instruments, they are global communities. Each project involves thousands of scientists, engineers, and software developers from dozens of countries, representing a fundamental shift in how we conduct the science of the sky. We have entered the era of big data astronomy, where the challenge is no longer gathering enough light, but managing the flood of it. The legacy survey of space and time alone will generate over 20 petabytes of data, a volume of information so immense that no single university, no single nation, can hope to process or understand it all. This sheer scale forces a new paradigm, one built on open data and radical collaboration. The findings from these telescopes will not be locked away in private archives for a privileged few. They will be released to the world, creating a living, digital sky available to anyone with an internet connection and a question. A high school student in Nairobi, an amateur astronomer in Buenos Aires, a researcher at a small college without a major telescope, all will have the same access to the cosmos as a professor at the world's largest observatory. This is a powerful democratization of discovery. It fosters a more transparent and inclusive scientific community where breakthroughs can come from anywhere, and the entire process, from raw data to final analysis, is open for scrutiny and contribution. Yet this new model also brings complex questions. In a field where traditional credit has often gone to the individual or the small team who first points a telescope and analyzes the results, how do we acknowledge the work of thousands? When a discovery is made by sifting through a public database that thousands of others are also exploring, who gets the credit? It challenges our very notions of scientific authorship and priority. The answer is evolving, leaning toward a culture that values the collective infrastructure as much as the individual insight. It highlights a profound truth: understanding the hidden universe is no longer a solitary pursuit. It is a collective human endeavor, a monumental project that requires shared tools, open doors, and a fundamental commitment to the idea that the cosmos belongs to everyone. The light may be bent by gravity, but its meaning is built by community. But the cosmic lens may have even stranger stories to tell, stories written in the language of speculative physics. The distortions we observe are born from the gravity of ordinary matter and dark matter. But what if the universe contains structures born from the wilder edges of Einstein's equations? Theoretical physicists have long explored the possibility of objects like wormholes, hypothetical tunnels through spacetime, or cosmic strings, infinitely thin defects in the fabric of the cosmos left over from its earliest moments. If such entities exist, they would warp spacetime in profoundly unusual ways, and that warping would leave a ghostly signature in the light passing by. A wormhole, for instance, might not require a massive galaxy at its throat to bend light. Its very geometry could create a pair of identical, magnified images of a distant object with no visible lensing mass between them, a cosmic mirage with an empty center. The magnification pattern might be distorted in ways that defy the clean predictions of a simple gravitational well. These ideas lie firmly in the realm of theory and imagination, yet they serve a crucial purpose. They stretch the tool of gravitational lensing to its absolute limit, asking what kinds of anomalies we should even look for in the data. They transform our sky from a map of known objects into a hunting ground for the profoundly unknown. As our surveys grow more precise, cataloging billions of subtle distortions, we will inevitably find outliers, lensing events that do not fit the standard model. Most will be explained by complex arrangements of ordinary dark matter, but a persistent, unexplained anomaly could one day become a signal. It could be the hint of something stranger, a kink in spacetime or a doorway to elsewhere, revealed only by its shadow on the bent starlight. This search is not about confirming science fiction, but about using the universe's own light to test the most extreme consequences of our own physical theories. It reminds us that every tool we forge to see the hidden cosmos also becomes a probe for the impossible, asking the oldest light to illuminate the newest ideas. The story of Starlight bent by gravity is ultimately a story about seeing differently. From the first warped images of distant quasars to the vast statistical maps of dark matter, this cosmic trick has transformed our entire perspective. We have moved from simply observing the lights in the sky to actively interpreting the curvature of spacetime itself. This journey, from Einstein's brilliant prediction to the torrent of data from next-generation telescopes, reveals a universe where the most powerful tools are not always built by human hands. Gravitational lensing is both a magnifying glass, bringing the faintest glimmers of the early cosmos into focus, and a cosmic scale, weighing the invisible scaffolding that holds everything together. Through it, the intangible has become tangible. We do not see dark matter, but we map its contours. We do not touch dark energy, but we measure its push across billions of years. Our understanding now comes not from direct sight, but from following the profound logic of gravity to its inevitable conclusions. As we continue to peer through these natural lenses scattered across the heavens, a deeper truth emerges. The universe's greatest secrets are rarely locked away in some distant vault. More often, they are hidden in plain sight, woven into the very fabric of reality, waiting for the right tool and the right perspective to bring them into view. They wait for a mind to ask a new kind of question and for a patient observer to decode the whispers in the bent light. If this journey through cosmic mirages has shifted how you see the night sky, we would love to hear your thoughts. Share them below and subscribe to join us as we continue exploring space's greatest mysteries.